Hi, let's start these pharmacology lectures. The first one is on ionization of drugs from general pharmacology. The learning objectives includes to identify ionized and non-ionized forms of either weak, acidic or basic drugs. It's important to note the difference between a protonated and non-protonated or unprotonated forms of acidic or basic drugs. The whole concept of ionization is depend on Henderson's Hasselbalch's equation in estimation of percentage of ionization. Finally, we calculate the percentage of ionized or non-ionized forms of an acidic or a basic drugs when they are kept in acidic or more basic media. That's the objectives. Let's start with the discussion of ionization of drugs, which is primarily dependent on the surrounding pH. Every single drug which we discuss have a tendency to get ionized depending on either it's weak acidic or basic drug. A weak acid or weak base is having a special feature of trying to remain in both ionized and unionized state. The strong acid and strong base are primarily ionized. So depending on the surrounding pH, the acidic drug, weak acidic or weak base can remain ionized, unionized. I'll show you. This is the acidic drug, which is non-ionized, no charge. It can donate proton. An acid is a proton donor. Proton is hydrogen, which is dissociated or donated. It becomes ionized. A minus is ionized. So an acidic drug, weak acidic drug can remain in non-ionized, no charge, or ionized with negative charge, depending on the surrounding pH. The same applies to weak basic drugs. A base is a substance which accepts protons, and when it accepts proton, it becomes ionized. You have plus here, BH plus. And the base can be B, which is non-ionized, or with the charge B plus, depending on the surrounding pH. Point to note, the HA and B forms of the acidic or basic drugs, they are non-ionized, no charge. They are lipid soluble and cross the membrane easily. Whereas the charged negative or positive charged, they are attracting water molecules, they are water soluble, cannot cross membrane easily. This is the key. And now protonated forms means when there is a hydrogen attached to an acidic or basic drug. So protonated forms, HA could be non-ionized, BH plus here could be ionized. Similarly, the unprotonated could be ionized or non-ionized. The whole theme of this discussion is based on Henderson's Hasselbalch's equation, which is stating that the protonated or unprotonated form of a drug ionization status can be given based on this equation, which says log to the log with protonated over unprotonated is equal to pKa minus pH, and the discussion is log to the base of 10. When we are not comfortable with doing calculations with logarithm, I want to take out the log. Look at this. Log to the base 10 x is similar to log to the base 10 protonated, unprotonated, and pKa minus pH is similar to y here. So I'm taking out log now. When I take out log, it becomes x. X is here, protonated, unprotonated is equal to 10 to the power y. So this is 10 to the power pKa minus pH is equal to protonated, unprotonated. This is nothing but the derivation or extension of Henderson's Hasselbalch's equation, the primary equation, which applies to both acidic and basic drug and helps in estimation of ionization status. And now note down again, Protonated form of acidic drug is non-ionized. Protonated form of basic drug, which means protonated with the hydrogen, is ionized. Now we go to this finally review point, that this is Henderson's Hasselbalch equation. We have derived and made it comfortable for our pharmacology. And now look at here, 10 to the power pKa minus pH is equal to protonated, unprotonated for both acidic basic drugs. And now the protonated form for acidic drug is non-ionized. You have protonated HA. That's why it is in the numerator. The unprotonated form of acidic drug is without proton ionized, so it becomes numerated. This is the formula for acidic drug. Similarly, for a basic drug, we have the protonated form for a basic drug here is charged ionized, whereas the unprotonated form for basic drug is non-ionized without any charge. So we have two formulas from this Henderson Hasselbalch equation, one for acidic, one for basic. If you want ionized, unionized. If not, we can have protonated, unprotonated for both acidic, basic. Let us calculate the ionized and unionized forms of the acidic or basic drug. We need three things. We need to know the pKa of a drug, unique property of a drug. We need to know the surrounding pH, and we also need to know the nature, acidic or basic drug, which we have to know. Now, for example, some of the examples of acidic drugs here are given. The pKa is, in these most cases, is less than 7, but it is not always true. Certain acidic drugs like acetaminophen have pKa more than 7, which means that you need to know the drug is acidic, basic. Cannot always guess on pKa. Similarly to the basic drugs, you see pKa of most basic drugs are more than 7. However, there are certain drugs like diazepam, which is a basic drug, but the pKa is less than 7. The point is, you have to know a drug is acidic or basic, which should be given in question. You can make educated guess, but it's better to know it. Now, pKa, what is it? It is the pH at which the ionized and unionized are 50-50%. When the pKa minus pH is 0, which means they are same, and they are 50-50%. Now, this is the key. When the pKa minus pH, this is for acidic drug, when they are negative, -1, -2, or -3, which means that the acidic drug is kept in more basic medium. Acidic drug donates proton. Basic medium is accepting, in other words, proton. That's why it can donate proton and become more ionized. More means it could be 90, 99, or 99.9. So it is more ionized. Similarly, if we have pKa minus pH for acidic drugs, if it is 1, 2, or 3, which means the acidic drug is kept in more acidic medium. Acid wants to donate, but the surrounding more acidic medium do not take or interested in accepting any proton, because it has itself more proton. So it remains undissociated, which means non-ionized. Acidic in acidic, non-ionized. More non-ionized. More means it could be more, which means 90, 99, or 99.9, depending on these three differences of pH. Let's take the example of this. There is an acidic drug with a unique property of pKa 5 kept in surrounding medium of urine, which is 7, which is relatively more basic. When the difference is 2, which could be -2 or +2, you see here, when it is -2, it is 99% and 1. If it is +2, it is 1 and 99. So all we know, when the difference is 2, it's 99 and 1. And what is 99 and what is 1? Which means when an acidic drug is kept in more basic, they are more ionized. More means more than 50. More than 50 here is 99%. So 99% ionized. Similarly, we have a pKa minus pH for basic drug. When pKa is equivalent to pH, they are 50% ionized. When a basic drug with certain pKa is kept in this surrounding, when the pKa minus pH is 1, 2, or 3, which means the surrounding is more acidic, the drug is more basic. What it means is that the basic drug is kept in more acidic medium. So the acidic medium wants to donate proton, the basic drug wants to accept, so they become more ionized. So more is again 90, 99 or 99.9. And in the contrast manner, if the pKa minus pH, a basic drug is kept in more basic, it could be -1, -2, or -3. In situations such of this base in more basic, base wants more proton, but the surrounding medium has no proton, so it will, in such cases, remain non-ionized. That's all about base in base, more non-ionized, acid in acid, more non-ionized, but the acid in base or base in acid, more ionized. Take an example. Basic drug with pKa of 9.8 kept in surrounding medium of 6.8, relatively more acid. Now, basic drug in acidic medium. This is base wants proton, acid is ready to donate proton. So it becomes, in other words, more ionized. More means it could be 99.9, 90, or 99, depending on the difference. In this case, the difference is 3 between pKa and pH. So it is, in other words, 99.9 ionized. And that's all. The summary of this discussion is, first thing to know is the difference between pKa and pH. It could be 1 or -1. If that is the situation, the ionization status is 90% and 10%. So we have to find out the ionized is 90 or non-ionized is 90, which we will come to. If the difference is 2 or -2, it is 99 and 1%. Ionized is 99 or non-ionized is 99, we have to find out. And similarly, when the difference is 3, it's 99.9 and 0.1, which could be ionized or non-ionized. We'll find out. Acidic drug in basic medium, and they are, in other words, primarily in ionized form. So, in other words, or a basic drug in acidic medium, they are primarily in ionized form, which means acid ready to donate proton, base ready to accept, so they are in ionized form. More ionized, more means it could be 90, 99 or 99.9, depending on these the surrounding pH and pKa difference. And finally, when acidic is present in more acidic, or base is present in more basic, they are not ready to donate, so they are primarily in non-ionized form. Primarily, predominantly non-ionized could be 90, 99 or 99.9, depending on these three pKa minus pH difference. That's all from my side. Thank you very much.